what is an isotope? Atoms of the same element with different mass numbers or different number of neutrons. So an isotope is an atom of the same element with different numbers of neutrons. So we have the nuclear symbol notation. The top left number is the mass number, and the bottom left number is the atomic number. And we have the hyphen notation, which is the name of the atom, hyphen, and mass number. What is mass number? Yes, the total number of protons and neutrons. Basically everything in the nucleus. And the atomic number is just the protons. So we have different isotopes. So we'll have the same number of protons. It's carbon 12. It has 6 protons, 6 neutrons, and 6 electrons. And then we also have something like carbon 14. The only difference is the difference of neutrons. Here we have 2 additional neutrons. Everything else stays the same. And unless otherwise stated, we will assume that this is neutral atoms. In a neutral atom, the number of electrons equals the number of protons. These symbols are also derived directly from the element's name. So C for carbon. By the way, have y'all ever looked at the periodic table and encountered some weird naming conventions? For example, looking at the periodic table, iron, Fe. Where do they get Fe from? That'd be the old Latin name for iron. So ferrium, or ferrous, means containing iron. So some of these names come from Latin. So Fe is for ferrium. We just renamed it to iron later. Like tungsten is a capital W. It stands for wolfram, was the old name for tungsten. So again, looking at like lithium-6 versus lithium-7, the only difference is the number of neutrons. So in lithium-6, we have 3 neutrons, 3 protons. And in lithium-7, we have 4 neutrons instead of 3, but 3 protons, 3 electrons. We can also see partial Bohr model up above. So if you can recall, the first energy level can only hold 2, which means the third electron has to be in the second energy level. But we'll learn more about energy levels next time, or next unit. So chlorine-37. Again, I told y'all will need periodic tables for at least this unit and the next unit. Chlorine-37, what's the atomic number? right side, 17. So 17 protons. What is the mass number? $37. So remember that name up top is the hyphen notation. It's the name of the element hyphen mass number. So how many protons does it have? 17. How many electrons does it have? 17. So again, unless otherwise stated, we assume it's neutral. So the number of electrons balances out the number of protons, making it have no charge. And how many neutrons does it have? 20. So 37 minus 17 is 20. Unless if we were to write it in symbol notation, it'd be 37 on the top left and 17 on the bottom left, and Cl for chlorine. So, y'all remember what the definition of atomic mass unit is in AMU? How was the atomic mass unit defined? It was defined as 1/12 the mass of a carbon-12 atom. So this gets into general relativity. You probably all heard this equation, E equals mc squared. Do y'all know what that means? What does E equals mc squared mean? Well, what is E equals mc squared? Energy is equal to mass times the speed of light squared. So energy and mass have an equivalence. If you have a lot of energy bonded in one place, is equivalent to having mass in that place. So if you can trap energy into one location, such as binding protons together with a strong force, it creates mass. This is advanced stuff in general relativity. Basically what that says is protons don't have a constant mass. Whenever you take a proton and bind it in a nucleus, its mass changes because you're adding energy to keep it bonded there. So what this means is that the AMU is not going to be precisely equal to the number of protons and neutrons. So, for example, if we remember, one proton has a mass of like 1 AMU by itself. But if we look at it in here, we see that one proton, even this is wrong because of the definition. The definition has changed too. But the mass of a proton actually changes based on what element is in. We will be using the old definition of AMU. 1 AMU is equal to exactly 1/12 the mass of a carbon-12 atom. It's known as relative atomic mass because of relativity. Because of the binding energy also accounts for some mass. Y'all know what a proton is made of? You don't know subatomic atomic advanced particle physics? I haven't learned that. I'll have to take my physics class. So I find this fascinating. Y'all know that almost all the energy is not, all the mass doesn't come from mass. You don't need to know this, but a proton quartz. So a proton is, again, you don't need to know this. A proton is actually 2 up quarks and 1 down quark. So there are actually particles smaller than a proton. And a neutron is 2 down quarks and 1 up quark. So whenever a proton becomes a neutron, one of the up quarks becomes a down quark, and an electron is given off. It's a advanced particle, but if you actually weigh the mass of a quark, you find out that the actual mass of the particles does not equal the mass of the proton. It's actually the binding energy. So we have 2 up quarks and a down quark. They're bounded together by strong nuclear force and gluons. The entire mass of a proton comes actually in the binding energy between the quarks. And when you add another proton to it, you get strong nuclear force adding to it. My point is mass is not as complicated. You can't just take the mass of all the protons and add them together. The mass of a proton is a constant. So average atomic mass is the weighted average of all the isotopes. This is the number you see on the periodic table. So it's an average of the isotopes. Now, even though I said you cannot treat a proton as having exactly 1 AMU and a neutron as having exactly 1 AMU of mass, for the purpose of this class, we will be doing that to make math easy. Just know that in real life there is subtle differences, but for the purpose of doing chemistry, at least at a high school level, it makes no difference to our math. So if we have 2 isotopes, mass of one isotope, or the mass of one isotope times the percentage plus the mass of another, divided by 100 to get rid of the percentage. Better just do an example. So calculate the atomic mass of oxygen if its abundance in nature is 99.76% and 0.04% for oxygen 17, and 0.2% of oxygen 18. So to make this easier, we are going to assume, so let's make some assumptions. We will assume in this class 1 proton equals 1 AMU and 1 neutron equals 1 AMU, and electrons don't contribute to mass. So we have 99.76% of oxygen 16. We have 0.04% 4% of oxygen 17, and we have 0.20% of oxygen 18. Using these assumptions, what would be, so this is the isotope, this is the percent abundance. What would be the mass of oxygen 16? Okay, instantly tell me. What would be the mass of oxygen 16, assuming one proton is 1 AMU, one neutron is 1 AMU? What does this number right here represent? The number of protons and neutrons, also called the mass number. 16 AMUs, 17 AMUs, 18 AMUs, hence the reason they call it the mass number, the number of protons and neutrons. So if we wanted to calculate the average atomic mass, the average atomic mass, I don't really like how they're showing it in this PowerPoint because it has to divide by 100. Let me show you how they do it first. They say we take the mass of 16 AMUs, multiply it by the percentage, plus so average. So we have 16 AMUs times 99.76% plus 17 AMUs plus 18 AMUs times 0.20. And to get rid of the percentages, we divide by 100%. So we have to get rid of the percent units. I personally, because I have done so much math, I go ahead and convert the percentages anyway. You could have done this as 16 AMUs. So 99.76% is the equivalent of 0.9976. So I already go in and divide it by 100. It depends on if you're good at math. If you're not good at math, I recommend you keep the divide by 100 in. So 0.0004 plus 18 AMUs, and that would be 0.002. It's very easy to make a mistake. If you go ahead and plug it in, I'm just used to doing it like this. So I recommend actually doing what they say. You just write in the percentages. This percent sign will cancel out all these percent signs. Either way you do it, you're going to get the same answer. and you should get 16.0044 AMU. If you look at the periodic table, you'll notice that we're slightly off. It says that the correct value is 15.9994. So if we were to round this to 4 significant figures, this would be 16.00 AMUs. And if we were to take the periodic table, 15.994 AMUs, and we round it to 4 significant figures, there's additional 9 in there, 9994, we round it to 4 significant figures, that is 16.00 AMUs. The periodic table I give you is more precise, but within 4 significant figures, these numbers match. Let's find a really weird one. Iron's weird. So, iron isotope, percent abundance. So, we have 5.845%, while iron atoms are iron 54. We have 91.754% is iron 56. 2.119% is iron 57. And 0.286%, all iron atoms, are iron 58. So the most common isotope, over 90% of all iron atoms, are iron 56. The second most abundant is iron 54. The third most abundant is iron 57. And the fourth most abundant is iron 58. So the mass number tells us our approximate mass. So to figure out the average atomic mass, we would do 54 AMUs times 5.845% plus 56 AMUs times 91.754%. And then we do plus 57, running our room, 2.119. Then we add 58 times 0.286% and divide all that by 100% to cancel out the percent units. and we get an average of 55.91225 AMUs is the average. Looking at the periodic table, shows that the average is 55.845 AMU. So, or assumptions of it proton being 1 does get us slightly off from the true value. But again, for the purposes of this class, this is close enough. If we were to round this number, for almost all the atoms, that tells us what is the number 1 atom, right? Or isotope. If we were to look at this periodic table, so if we were to look at the periodic table and round it to a whole number, that would be 56 AMUs. So that tells us that iron 56 is the most common isotope. Does that make sense? This does not work on every single one. Let's do a weird one. Copper is weird. So let's do copper. So 63 copper, 64, and 65. So the percent abundance is 69.7%. Synthetic. Man-made. Doesn't exist. This is synthetic, or 0%. Which means we can remove this from the periodic table. This means radioactive and only exist briefly. It's unstable. Unstable isotope. Doesn't exist in nature. So radioactive only exists briefly, unstable isotope. So we really only have 2 isotopes found in nature. So again, we go ahead solving it. The average atomic mass, which means if we had a collection of copper, we would expect 69.17% of the atoms to be copper 63 on average, and 30.83 would be copper 65. So we would have 63 AMUs, 69.17% plus 65 AMUs times 30.83%. We need to get rid of the percent sign so that our answer is only in AMU, so we divide by 100%. And we get an average of 63.6166 AMUs. And looking at the periodic table, see how accurate we got. It's 63.546. So again, very accurate. We are off slightly, but that's irrelevant. We're both, if we round this to the nearest whole number, we would see that copper 64 appears to be the most common isotope of copper. The reason for this as being wrong is because carbon 64 is unstable, and we have a very huge difference between 63 and 65, which places it somewhere in the middle. I won't ask you to memorize the exceptions. Copper is I think the only true exception that I can remember off the top of my head. If you look at the periodic table, and basically, if you end up with a number that is like 8 or 9 here, you're almost 100% guaranteed you're going to wind up with something like this. If you end up looking at the periodic table, and you see an element that has a 0.5 to where it's situated between a 63 and 64, halfway in between, that tells you this is probably an exception. So let's look at it. Atom. So carbon, very close to 12. That tells you carbon 12 is very most likely the main isotope of carbon 12. Nitrogen, 14.006, tells you nitrogen 14 is the most likely common isotope. Oxygen, 15.999. Again, oxygen 16, number one isotope. Fluorine, same thing, 18.9984. That tells you that fluorine's most common isotope is fluorine 19. If we were to keep going, sodium is 22.989. That is so close to 23. Here we start getting off, so 24.3. The 0.3 would tell me maybe 24 might not be it. So let's look that up and confirm and see whether or not magnesium. So isotopes of magnesium, we see that 25 is 10%, 26 is 11%, and where's the other one? 24. So 24 is the most common one with 78.7. So in this case, if you round it, it turned out to be correct. If you were to round it this down to a whole number, 24 is correct. Aluminum, and it's so close to being 27, you can just assume that that's it. All of these, chlorine is right in the middle, so 35.45. Let's check and see if that rounds correctly. I want to say copper is like one of the only exceptions I know of. Let's see if chlorine works out. So 75% is chlorine 35. So if you rounded that number, you would get the correct isotope. So besides copper, I really can't think of too many examples that zinc might actually be it. It's really close in the periodic table. So if we round zinc to the nearest whole number, 65, zinc 65. Zinc 65 doesn't exist. Zinc 64 is the most abundant, and we get these. So zinc is another common exception. I'm not going to do that on the test or anything. It's going to be straightforward. You don't have to memorize the exceptions. Just if you want to find the most common isotope, you can round these numbers to the nearest whole number, and that's the mass number of the most common isotope. So you take, so nitrogen rounds to 14. Nitrogen 14 is the most common isotope. So the importance here is in nuclear chemistry. So in nuclear chemistry, you need to know the exact isotope. In ordinary chemistry, isotopes don't affect chemistry at all. So let's do an example of some nuclear chemistry. We don't really do too much. So let's look up hydrogen reaction and sun. This is a straightforward equation. There we go. So we have, I'll remove this in a second. Deuterium plus tritium. So in the, I put, should be H. So we have hydrogen H2, and we have hydrogen 3. So deuterium and tritium. In the sun, they fuse together. This is fusion. So the protons come together. So this tells us it's helium. This has 1 neutron. This has 2 neutrons. Didn't want to get past that. This is emitting a neutron too. One is simple reaction. But when combining them together, so what happens is this gets 2 neutrons. So this has 1 neutron, this has 2 neutrons. This helium nucleus gets a neutron, and then we have 1 neutron that flies away. So in the sun, helium is hydrogen is fusing together to make helium. This is how all the atoms in the universe are created in the sun. It's just constant reaction after reaction of atoms coming together to make new atoms. This neutron would come in, so we have hydrogen, so our normal 1 proton with 1 electron flying around it. And this will capture a neutron and go to deuterium, where we have a proton and a neutron with 1 electron going around it. And this can gain another neutron, and then deuterium and tritium will combine together to make helium, which gives up another neutron. This is how all the atoms in chemistry are made. They don't just exist, they all come from hydrogen. At one point, it was a hydrogen atom that had come together. We get higher up atoms and isotopes being made. We also have radioactive decay that I'll go into a little bit. But Let me finish. So this is actually them measuring. So we have a device called a mass spectrometer that can actually separate atoms out by their mass, and you can actually count how many chlorine versus chlorine 35 versus chlorine 37 atoms there are. If you're in physics, we'd actually learn the mathematics for this. How they actually weigh it is they have a magnetic field, and we strip off the valence electrons, and thus we can separate it based off of mass and electrical charge. They'll deflect. The heavier ions will deflect more than the lighter ones. Yeah, it looks like mercury is definitely going to be, what's mercury say on the 200.59, which would round to 201, which is off. The transition metals are exceptions to everything. By the way, transition metals, you ever hear me say it? This from here, this in the middle are called the transition metals. There are exceptions to a lot of things, and most of the chemistry we do will not involve them. Here. So using the periodic table, complete and fill out this chart. So what is the element on the first row? So this would be oxygen. How did you know that? So first one is oxygen. We know that because the number of protons is 8. Its symbol is O. Atomic number is 8. Atomic mass will be 16. Its charge is going to be 0. So what would potassium symbol be? Okay. What would be its atomic number? 19. So we take 39. For atomic number, 19 is just the number of protons. So we just look at the periodic table. It's 19. What would be the number of protons? 19. That's what atomic number is. What would be the number of neutrons? So we take 39 minus 19. So atomic mass minus atomic number gives you the number of neutrons. And what would be the number of electrons? It would be 18. So the charge here indicates this is a plus one atom. So that means it has one more proton than it does electron. So Br is the element for bromine. Looking at the periodic table, it's number 35. What would be the atomic mass? So it's the atomic number plus or it would be the number of protons plus the number of neutrons. So the number of protons is 35, same as atomic number. So 35 plus 45 is 80. What would be the number of electrons for this? So if it has a charge of -1, that means it has one additional electron that has protons. So it has 36. Someone else. What would be the name of the element on the bottom? Zinc. Its symbol is Zn. We know this because the atomic number is 30. And looking at the periodic table, number 30 is zinc. What would be the number of protons? Well, that's the same thing as atomic number. And what would be the number of neutrons? That seems off. We'll look at that. Wow. Now that seems off.